Chapter 20. Many electron atoms. Section 20.2. Electron spin and Pauli exclusion principle. Every electron has an intrinsic angular momentum that originates from its constant spinning about the x, y, and z axis that cross the center of the electron. A spinning electron can be viewed as an electric current loop, which produces a magnetic moment. The shorthand notation for the three-dimensional electron spin operator is lowercase s, topped by a caret symbol. The z component of s is denoted by s sub z. The z component of the spin of an alpha electron is positive by definition. The z component of the spin of a beta electron is negative by definition. The magnitude of the angular momentum of the electron spin is the square root of 0.75 times h bar. This is because the spin quantum number s is 1/2 for both alpha and beta electrons. And when s squared operator is applied to alpha and beta, the eigenvalues are the same. They are both h bar squared times s plus 1. So when we apply s squared to alpha, we get 0.75 h bar squared alpha. When we apply s squared to beta, we get 0.75 h bar squared beta. Again, it's just 0.5 times 1.5 is 0.75. So we have this spin angular momentum squared equal to 0.75 h bar squared. We can take the square root for both sides. The magnitude of the three-dimensional angular momentum is thus the square root of 3/2 times h bar, or it's approximately 0.866 h bar. The z component of the angular momentum of the electron spin is m sub s h bar. M sub s is the z component of the electron spin. M sub s can be negative 1/2 or positive 1/2. And therefore, we can apply this s sub z operator to alpha and to beta. We get two different eigenvalues, positive 1/2 h bar, negative 1/2 h bar. Alpha and beta denote the two spin functions of the electrons. They are always normalized. That means the integral of alpha star times alpha d sigma is 1. The integral of beta star beta d sigma is also 1. Here, alpha star is the complex conjugate of alpha, beta star is the complex conjugate of beta. And sigma is the spin coordinates of the electron. Alpha and beta are orthogonal to each other. So the integral of alpha star beta is 0. The integral of beta star alpha is also 0. Sigma, again, is the spin coordinates of the electron. You may imagine this sigma contains also three variables, a radius, a value of theta, a value of phi for the electron spin. The electron often has two different rotational motions. One is about the nucleus, and then you have r, theta, and phi as the coordinates. But there's also a spin about its own axis, and then you need another set of polar spherical coordinates to describe the electron spin. Intuitively, we proposed this e to the power of negative zeta r1 times e to the power of negative zeta r2 for the wave function of the helium atom, but we learned that that's a violation of postulate 6, because in postulate 6 we know the wave function of two electrons must be anti-symmetric under the exchange of these two electrons. So now, what if we add some spin function? Intuitively, we just add the spin function this way. We add alpha 1 here to specify the spin of electron 1, beta 2 here to specify the spin of electron 2. We're assuming electron 1 has a alpha spin, electron 2 has a beta spin. But unfortunately, this wave function is neither symmetric nor antisymmetric, because if we exchange the two electrons 1 and 2, well, we can see this is what we got. These two are different, and these two are also different. So it's neither symmetric nor anti-symmetric. So we must modify this wave function to comply with postulate 6 by ensuring that the wave function change sign under the exchange of two electrons. So we have to have this. One of the linear combinations of these two functions is antisymmetric under the exchange of the two electrons, and thus complies with postulate 6. So you can see over here, this is e to the power of negative zeta r1 alpha 1, e to the power of negative zeta r2 beta 2, and here we have e to the power of negative zeta r2 alpha 2, and e to the power of negative zeta r1 beta 1. So look here, this somehow indicates electron 1 is alpha, electron 2 is beta. Now this is kind of just reversed. Electron 1 is beta, electron 2 is alpha. So we can somehow do a linear combination of these two. One of the linear combinations is this. We just simply take the difference between these two. So the first term, electron 1 is alpha. The second term, electron 1 is beta. The first term, electron 2 is beta. The second term, electron 2 is alpha. Now, since the exponential function is the common factor, we can take this common factor out. We have the product of two exponential functions, e to the power of negative zeta r1, e to the power of negative zeta r2. We know this is symmetric under the exchange of two electrons. And then we look at the spin part. The spin part is alpha 1 beta 2 minus alpha 2 beta 1. Somehow this is anti-symmetric, because if you exchange 1 2, it becomes alpha 2 beta 1 minus alpha 1 beta 2, which is the opposite to this original spin part. Therefore, under the exchange of two electrons, this spatial part that depends on the spatial coordinates remains unchanged. So this two exponential functions together is symmetric. But the spin part is anti-symmetric, which changes sign when we exchange the two electrons. So overall, this wave function becomes anti-symmetric under the exchange of two electrons. And therefore, this wave function complies with the quantum mechanical postulate 6. We can easily verify if we exchange 1 and 2. We have psi of R2 and R1. And then I need to replace R1 with R2, R2 with R1, 1 with 2, 2 with 1, 2 with 1, and I replace this 1 with 2. Now let's compare this wave function and this wave function after the exchange. The exponential function here, this 2, are the same as this 2. But now look at the spin part. Negative alpha 2 beta 1 becomes positive alpha 2 beta 1. Positive alpha 1 beta 2 becomes negative alpha 1 beta 2. Now we changed the sign. What if the two electrons in the 1s orbital of the helium atom were forced to have the same spin? For example, both are alpha spin. Then the wave function of this will have to become this. We need to change beta to alpha. And then we get the wave function equals 0. And that means two electrons in the 1s orbital of helium must have different spins. If they have the same spin, even this wave function doesn't work. You get a value of 0. The probability is 0. Now, more generally, Pauli exclusion principle states that two electrons in the same spatial orbital must have different spins, because otherwise the wave function would be 0. Exactly 0. The probability of finding two electrons with the same spatial quantum number and the same spin quantum number is just 0. And when the wave function is 0, the squared modulus of the function is 0, the probability density is 0, and then the probability is 0. So in the end, no two electrons in the same spatial orbital can have the same spin. Well, also you can say two electrons with the same spin cannot occupy the same spatial orbital. Pauli exclusion principle states that two electrons in the same spatial orbital must have different spins, because otherwise the wave function would be 0. For the same reason, two electrons with the same spin cannot occupy the same spatial orbital. And more generally, it's less likely to have electron appear close to another if they have the same spin than if they have opposite spins. And this phenomena is called exchange hole, depicted in this graph. So if you have a alpha electron over here at this position, it's unlikely to have another alpha electron getting close to this alpha electron, because two alpha electrons can never have the same spatial quantum numbers. And that means they can never occupy the same spatial orbital. And because of this, the density of the second electron may drop significantly when it's close to the first electron with the same spin. And this results in a smaller electron-electron repulsion. So two alpha electrons can better stay away from each other because of this Pauli exclusion principle. And therefore, we have a lower energy between two alpha electrons than the energy between one alpha and one beta, due to the smaller electron-electron repulsion. And this energy decrease is called exchange energy. And here's one example. If we excite one of the electrons in the helium to the 2s orbital, the triplet electronic state has lower energy than the singlet electronic state, because in the triplet electronic state we can have the two electrons with the same spin. In the singlet state, the two electrons have opposite spins. Now let's look at the excited helium atom in detail. When an electron is excited to the 2s orbital, there are 4 different arrangements that include a triplet electronic state with a degeneracy of 3 and a singlet electronic state. The triplet electronic state of this 1s1, 2s1 electron configuration has lower energy, because in the triplet state, the two electrons may have opposite spins. We have 3 functions over here. They are degenerate. So we can see all these 3 wave functions are a product of the spatial part and the spin part. The spatial part is the same. It's f1 of r1 times f2 of r2 minus f2 of r1 times f1 of r2. F1 and F2 denote the spatial functions of 1s and 2s orbitals. And you can see 1, 2, 3, these 3 are exactly the same. Now let's look at the spin part. It can be alpha 1, alpha 2. Both electrons are alpha electrons. Beta 1, beta 2. Both electrons are beta electrons. Well, over here, this is kind of a little strange. This is alpha 1, beta 2 plus alpha 2, beta 1. This is due to the quantum effect. Electrons must be indistinguishable. So this wave function must be written in a way that it's anti-symmetric. And over here, the spatial part is anti-symmetric. the spin part must be symmetric. So over here we have to write alpha 1 beta 2 plus alpha 2 beta 1 to make sure that this wave function remains unchanged when we exchange two electrons. So if you replace 1 with 2, 2 with 1, 2 with 1, 1 with 2, you get the same spin part. Same here. If you exchange 2 and 1, it remains unchanged. If you exchange 1, 2, this spin part remains unchanged. But the spatial part is anti-symmetric. Alright, so we have a product of the spatial part and the spin part. Alright, so if the spatial part is anti-symmetric, the spin part must be symmetric. So now we have the anti-symmetric spatial part and the symmetric spin part. And overall, the wave function is anti-symmetric. Now let's look at the spin part. Alpha 1, alpha 2, beta 1, beta 2, and finally alpha 1, beta 2, and alpha 2, beta 1. They all share the same spin quantum number. S is 1. So S is 1 for the 3. Alright, and when S is 1, we have a degeneracy of 3, because the Z component can be from -1 to 1. So the Z component of the electron spin is over here. This is 1, this is -1, and over here this is 0. So all three share the same spin quantum number. S is 1. But now M sub S can be -1, 0, and +1. Finally, let's look at the singlet, in which S is 0, M sub is 0. We have a degeneracy of 1. Let's look at the wave function of the 1s1, 2s1 electron configuration here. Now this time, the spatial part is symmetric. The spin part is anti-symmetric. Overall, the product is anti-symmetric, in compliance with postulate 6. So it's possible to calculate the average electron repulsion using postulate 4. In postulate 4, what we need to do is we need to have two integrals on the top and the bottom of a fraction. On the bottom, it's the integral of psi star times psi, and on top it's the integral of psi star multiplied by the repulsion operator applied to the wave function. So we can compare this wave function and this wave function, alright, or just any one of the three, and evaluate their average repulsion energy. You will see when we use this singlet wave function, we have a larger repulsion than the triplet. And again, that's the so-called exchange energy. The electron repulsion is smaller in the triplet electronic state here than the corresponding singlet state over here.